Now into problem 6.71 here, I have a little sketch of the drawing again with the control volume in red, the normal vectors pointing out of the control volume, and the flow rates, so Q1, Q2, and Q3. Q2 and Q3 are pointing out at an angle, and I also drew the coordinate system I'm going to define in red, so we have the positive x direction and the positive y direction. The next step again is to start with the conservation of mass, so we know that 0 is going to be equal to the rate of change of the mass inside the control volume plus the ingoing and outgoing fluxes. We arrive at the expression 0 is equal to rho v1 minus 1, again because we're going into the control volume A1 plus rho v2 A2 plus rho v3 A3. This means that our flow rate is going to be Q1 is equal to Q2 plus Q3, which means that we can solve for Q3, which will be 2.5 liters per minute. Now the next step, if we draw a streamline, starting from point 1 to point 2 and from point 1 to point 3, we can compute the pressure at P1 and at P3. From the streamlines, we can use Bernoulli's equation. So P2 is equal to 1/2 rho V2 squared plus rho GZ2 is equal to P1 1/2 rho V1 squared plus rho GZ1. Now, because the variation in height is so small, we can approximate it as being 0, and we can isolate for P2. Now, because it's easier to work with standard units here, I'm going to be computing the area, so area 1, area 2, and area 3. And I will also be calculating the velocity. So the velocity v1, v2, and v3, these are all going to be needed in Bernoulli's equation. And also, for the sake of simplicity, converting the P1 as being 140 millimeters of mercury into standard units. Now that we calculated on all the unknowns, we could calculate P2, and P2 will be equal to 17.58 kilopascals. Using the same logic and procedure as finding the pressure at P2, we could also find the pressure at P3, and this will give us an answer of 694 pascals. Now that we've found all of our pressures, we can now use the conservation of momentum equation. That will be, again, summation of forces is equal to the rate of change of the momentum inside the control volume plus the ingoing and outgoing fluxes. Now the next step here is going to be to find all the external forces that are acting on our system here, or on our control volume. So I did a little sketch right here, again with the same system of axes. So we have the positive, indicating the positive X and positive Y direction. And then we also have our external pressures, so P1, P2, and P3. Now that we have our little sketch here, we can write down that the summation of forces is going to be equal to P1A1J, and that's positive because it's in the positive direction, plus P3A3 cos theta 3, and that is in the positive X direction, so I, minus P3A3 sine theta 3 J, and that's because it's in the negative Y direction. Then again, minus P2A2 cos theta 2I, that's because it's going to be in the negative X direction, minus P2A2 sine theta 2J, again because we're in the negative Y direction. And then we will add our reaction forces, and here I'm just assuming that my reaction forces are going to be in the positive X and the positive Y direction. Now onto the next part of the conservation of momentum. This will be our ingoing and outgoing fluxes. So our ingoing and outgoing fluxes will be equal to minus rho v1 squared a1 j, and this is because it is incoming into the control volume, plus rho v2 squared a2 cos theta 2I. This is because the velocity coming out of point 2 will be positive in the x direction and is also leaving the control volume, plus rho v2 squared a2 sine theta 2j, again because we're leaving the control volume and we're leaving in the positive y direction. Then we have minus rho v3 squared cos theta 3I. This is going to be negative because even if we're leaving the control volume, we're leaving in the negative x direction according to the coordinate system I defined. And then finally, plus rho v3 squared sine theta 3j. This is going to be positive because, again, we're leaving the control volume and our velocity is pointing in the positive y direction. Now that we have our summation of forces and our ingoing and outgoing fluxes, we'll compute this for the x and the y direction. So here for the x direction, we'll have P3 A3 cos theta 3 minus P2 A2 cos theta 2 plus our reaction force Rx is equal to rho V2 squared A2 cos theta 2 minus rho V3 2 cos theta 3. And now replacing with all the known values, we get that our reaction force is going to be 0.15 newtons. Here the same procedure can be done in y to find the reaction force in y. So we look at the conservation of momentum and we'll get the following expression: P1 A1 minus P3 A3 sine theta 3 minus P2 A2 sine theta 2 plus the reaction force in y is equal to minus rho V1 squared A1 plus rho V2 squared A2 sine theta 2 plus rho V3 squared A3 sine theta 3. Computing again for all the known values, we get that our reaction force in Y is going to be minus 1.026 newtons. Now that we have the reaction force in X and Y, we can calculate the magnitude and the direction. This is just using some trigonometry, so we obtain that the magnitude of the reaction force will be 1.037 newtons. This is according to the direction that I have the little sketch on the left hand side, and this will be at an angle of 8.5 degrees. Again, this is in reference to the angle that I drew on the sketch.